Hello students, welcome back to A-Star Tuition channel. Today we'll learn about kinematics and we will start going to explain about the definition and quantities associated with that. Let's start. Now, I will begin the lesson by explaining how kinematics fits into physics. Now, as you know, physics contains several aspects, several branches. You can say, like for instance, mechanics, thermal, electromagnetic. Now, kinematic itself actually falls into the category of mechanics. Now, when you learn mechanics in high school, curriculum, whatever curriculum you learn, will usually divide mechanics into two parts. The first part is the one that we are working on today, which is called kinematics. And the second part is called dynamics. Now, what is the difference between kinematics and dynamics? The difference is, when you learn about kinematics, you learn motion, but without actually explaining the cause of motion, like forces. Whereas dynamics is actually dealing with the forces. So there is an inherent difference, because in dynamics we will actually use something called Newton's law to explain much of the underlying concept. Now, for kinematics, we actually do not use Newton's law whatsoever. So, without further ado, let's discuss kinematics. Okay, let me erase this and start with kinematics. Okay, so when we talk about kinematics, we always deal with motion, right? Now, when we talk about motion, there's always like quantities associated with motion. Let me lay out some of those quantities for you. Okay, so we have this thing called displacement, and we also have distance and velocity, speed, and then acceleration. Now, you might notice that I actually put these quantities in one column and these quantities in the other. Why do I do that? Because they actually belong to one particular classification of quantity, what we call as vectors. So this is a vector quantity. Okay. Whereas these two are known as scalar quantity. Now, in the video about vectors, you learned that vector quantity is a vector that is described not only by its magnitude, by its direction as well. As for scalar quantity, it's only magnitude. Now, our discussion today, we will limit ourselves to one-dimensional motion. So the notion of vector quantity and scalar quantity becomes not so much different. Yeah, not so much different in the sense that the difference is actually easily distinguished because of the fact that the motion is only two ways, one way or the opposite. So that's one-dimensional motion. So let me write it down here. So one-dimensional motion, 1D motion, is a motion in which the position of the particle can only be two ways, one way or the opposite. For instance, sideway motion, sideway motion, or sometimes we call horizontal motion. Now, there's also up and down motion, or sometimes we call vertical motion. So the motion will be restricted to one dimension in this discussion. Now, let's start to discuss about displacement. Okay. Now, for an example, let's take a look at this picture. You see there are actually 3 points, A, B and C, and they're separated by 50 meters each. B is 50 meters to the right of A, and C is also 50 meters to the right of B. And they are actually in one straight line, or we sometimes call it collinear. Now, a person is initially at point A, right? Now, the person, let's say the person walked from point A to point B, okay? Okay. Now, the person walked from point A to point B. What is the displacement of the person? Now, in order to answer that, let's just write down the definition of displacement. Displacement is actually change in position in a certain direction. Now, remember that we restrict our discussion to one-dimensional motion. So there's only one dimension. So you can either, so the motion is sideways or horizontal. So either to the right or to the left. Now, as you can see, the person initially is at point A, and then the person then moved to point B, and we can see that the change in position is 50 meters. So then we say, based on this definition, the person's displacement is 50 meters to the right. So the person's displacement is 50 meters to the right. Yeah. Now, what about the distance traveled? Now, the distance traveled, actually, we don't really care about the direction. So it is actually, you can define distance as the length of the trajectory or the path of motion. So let me write down the definition of distance. So distance is the length of the path of motion. Now, as you can see here, the path of motion is a straight line from A to B. And you can see that the length is 50 meters. So hence, we say that the distance is also 50 meters. Distance traveled 50 meters. This time, we don't really need to add this direction, yeah, because as I explained before, distance is not a factor, it's a scalar. So it's the length of the path, and you can see it's 50 meters. Okay, you can see from this example that there is no inherent difference between displacement and distance, except for the fact that for distance, we don't really say that it's moving to the right. Now, the magnitude is 50 meters, right? But then, let's change the scenario a bit, and you'll see why distance and displacement are not actually the same quantities. Yeah. Okay. Now, let's say that the person moves, let's say, from A to B, and then to C, and then move back to B. Now, in this case, the displacement with respect to the initial position, right, the change in position, is actually 50 meters to the right. So there's no difference between the displacement before and the displacement in this case. So we say that in this case, so the motion from A to B to C, and then go back to A, we still say that the displacement is still 50 meters. Displacement still 50 meters to the right. Now, however, when we talk about distance, it's actually not the same in this case. Because remember, distance is the length of the path of motion. In this case, the motion, the person starts from A to B to C and then go back to B. So you can see that the length of the path of motion is 50 plus 50 and then plus 50 again. So then the distance in this case is equal to distance traveled, yeah, equal to 50 meter. 150 meter, yeah, so 50 plus 50 plus 50, 150. Now, you can see that not only that distance travel is a scalar that has no direction, even the magnitude itself is different from displacement. So I want you to please make sure that you understand the distinction between displacement and distance. Okay, now let's move on to the next concept, which is about velocity. Velocity. What is velocity? Okay, velocity is actually rate of change of position. Rate of change of position. So it tells you how fast a particle or any object moves from one point to other. How fast the position changes with time. Now, when we talk about velocity, we always need to distinguish between two different concepts of velocity. Now, the first concept is just velocity, or sometimes it is called instantaneous velocity. Now, instantaneous, the word instantaneous is usually implied. Like, you don't really have to say the word instantaneous, but if you say velocity, then by default it means instantaneous velocity. But then there's also average velocity. They are related, but there's obviously a distinction between average and instantaneous. What is average velocity? Average velocity is simply the change in position factor per unit time. Now, the instantaneous velocity, rate of change position at any instant. So, therefore, the difference is about the time interval, so to speak. The time interval between instantaneous and average. Now, in general, let's say that a person is moving. The person is moving from position. Let's say this is the graph of position, function, time. Now, let's say that at this point here, let's say this is 1 meter, 2 meter, 3, and 4. And this is the time axis, the horizontal, yeah. So 1, 2, oh actually this is 2, 3, 4, and 5. Okay, let me draw a bit more straight. Yeah, okay. This is 1, 2, 3, 4, 5. And this is the time axis. Now, let's say that the position of the particle as a function of time looks like this. It starts from 0. It starts from 1. And let's say that it starts from 1 and then we draw this graph. Now, this graph shows that the particle is moving from time 0 to time 5, and the position changes from 1 to 4. Again, the time starts from 0 and ends at 5, and the position starts from 1 and ends at 4. Okay, now this is the position, and let me label with the unit which is meter, and this is the time label with the unit which is second. Yeah. Now let's calculate the average velocity for this motion. Now, average velocity is equal to the change in position factor over time. Now, in this case, because this is only one dimensional, you can see that the notion of factors is either, one way or another, like, sideways, horizontal, left and right, or vertical, up and down. So that in this case, you can see that the position is at 1 initially, And then finally it is at 4. So the change in position is 4 minus 1. 4 minus 1. And the time, you can see that it starts from 0 and then ends at 5. So 5 minus 0. So the answer is 3/5, which is equivalent to 0.6 meter per second. Now, if you notice, the notion of 4 minus 1 divided by 5 minus 0, in this case, is actually the slope or the gradient of a straight line that connects this initial position to final position. Yeah, let's draw the straight line. Now you can see that what we did here, I'm subtracting 4 with 1. That's the so-called rise. And also I subtract 5 with 0. This is the so-called run. So rise over run. And it gives you exactly the average velocity. So then it is actually the slope or the gradient of the straight line that connects initial position and final position. Yeah, so it's you can see that this is quite straightforward, yeah, if you are familiar with the concept of gradient. Now, what about instantaneous velocity or just velocity? Yeah, because remember, we don't really need to use the word instantaneous, because as I mentioned, by default when we talk about velocity, what we mean is instantaneous velocity. Now, when we talk about instantaneous velocity, the rate of change of position at any instant. So we have to pick at what instant you want to calculate the value. Now it could be the value of instantaneous velocity. Let me just erase the straight line from the average velocity, and let's keep the graph intact. Okay. Now you can see that this is a curvy line. Yeah. So it's not a straight line. So let's say I want to calculate my velocity at 3. So what do I do? Now what you need to do is that you need to draw or indicate or locate the position, yeah, at t equal to 3. Now after that, what you need to do is you need to draw like a straight line, a straight tangent line. Yeah. Now when you do that, this straight line will have its slope as well, its gradient. So then you can estimate the velocity at t equal to 3 by drawing a straight line, a tangent line, so to speak, from at this point, at point of interest, and then you calculate the gradient. So rise over run. So really, it's actually similar to the definition of average velocity, but the only difference is that the interval is very short. Now, you see that when we try to find the velocity, what we do here is we estimate the slope of the tangent line at this point. Now, so this is actually, we're talking about tangent line and how to calculate or estimate the slope of the tangent line. The idea of that is actually related to calculus, but since we don't use calculus in high school physics, we normally skip that part. But if you are familiar with that, you probably will have some nodding, acquaintance with this concept. Now let's talk about speed. Now, like velocity, we make a distinction between instantaneous speed and average speed. Now you can see that the difference is between instantaneous value and average value is similar to when we deal with velocity. Yeah. So then if you have the position function time, you can simply find the initial point, final point, connect with the straight line, even though the graph itself is not a straight line. Maybe the graph is like this, but you can just draw a straight line connecting the initial, final, And then from there, you divide the rise over run. Now, however, if you define that way, it doesn't seem like there is a difference between average speed and velocity, right? Now, let me give you an example in which you can see the distinction between average speed and average velocity, which is like this. Let me draw another example. Let's say that the motion is like this. Let's say the motion is a straight line, yeah? So, the motion is a straight line, one-dimensional, but what I mean is that it's linear in the sense that the position function time increase or decrease linearly, okay? Now, you can see that, again, at initial time, the position is at 1, and as you can see that this is the furthest position from the initial position. Let's say this is equal to 4, and then here this is 2. Okay, then let's say that the time is, this is 0 and this is 6. Okay, now what is the average velocity and what is the average speed in this case? For average velocity, again, we only look at the change in position with respect to the initial. So the initial position is 1. So we say that x of 0 is 1 meter. And the final position is 2. So x at 6 is equal to 2. So therefore we can say that the average velocity equal to 2 minus 1 over 6. So 1 over 6 meter per second. Now what about the average speed in this case? Well, average speed is about the distance. You need to find the distance. Now, is the distance traveled just 1 meter? Now, you can see that that's not the case, because you can see that there is a change in direction. So, like, remember, this is a one-dimensional motion. So motion is like one way, and then at a certain point, it turns around. Now, where does the turnaround occur? It occurs here. You can see that from time 0, let's say this is 4. Time 0 to time equal to 4, the position increase. So it starts from 1 and then it ends at 4. So you can see that from 1 to 4, from t equal to 0 to t equal to 4, the distance traveled is equal to 4 minus 1, 3 meters. Now on the other hand, from t equal to 4 to t equal to 6, you can see that the position decreases. Now the position decreases indicates that the particle has turned around, yeah, in the one-dimensional motion. So the distance from t equal to 4 to t equal to 6 is simply the difference between position 4 and 2, which is 2 meters. So now you can see that the distance traveled is equal to 5 meters. So 3 plus 2 equal to 5. What about the average speed? Yeah, average speed in this case, let me use the word speed like this. Yeah, this is equal to the distance traveled, 5 meters, you divide by the time, 6 seconds. So this is 5 over 6 meters per second. Now you can see the difference, yeah, between average velocity and average speeds. It's not necessarily the same thing, yeah, because for speed it's all about the distance, whereas velocity is about displacement, change in position. Now what about instantaneous speed? Instantaneous speed is actually kind of similar to average velocity. Yeah. So because we actually try to find how fast it's moving at a certain instant, the only difference is that we don't really need to specify the direction for speed. Yeah. Let's say at this point at t equal to 2, what we can do is we can just draw a straight tangent line to the graph. But then since the graph itself is already linear or straight line, then that straight line, we only need to find the slope of this straight line. So we don't really have to draw a tangent line. So similar to average velocity. So it's really about how fast a particle is moving at a certain time. Yeah. Now you can actually understand the difference between average velocity and instantaneous velocity, or average speed versus instantaneous speed, by considering this. Let's say that you are traveling from a city to another city. Now, when you drive, you don't always actually move with the same speed. Yeah, sometimes you move slow when when near the city. Near the city usually there's a lot of traffic, so you can't really drive too fast. But on the other hand, when you get into the highway, usually you speed up. When you speed up, you can see that you're moving faster than average. Whereas when you are in the traffic, you're moving less than the average. So the average is, again, you find for average speed, find total distance traveled over time. For average velocity, find the displacement or a change in position per unit time and specify the direction. Next, let's talk about acceleration. Now, like velocity, we actually have two distinctions to make, which is instantaneous value of acceleration and average value of acceleration. Again, remember that instantaneous is default. What I mean is that when someone mentions the word acceleration, by default, they mean instantaneous acceleration. It's defined as the rate of change of velocity at certain instant. So, like how fast is the velocity changing at particular time? Whereas average value in acceleration is simply you look at the change in velocity, could be in long term from one point to another, and divided by the time. Now, let's give you an example. Let's draw the graph of velocity as a function of time. Now, you can see that the velocity could be like this. Yeah? So you can see that the velocity is positive and it's getting faster, 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 and then it reaches its maximum value, and then later it slows down. Now, in order to calculate the average acceleration, let's say it doesn't have to start from initial. Yeah? It could be at any time. Let's say you calculate from t equal to 1 to t equal to 6, let's say. And let's say that this equal to the value of the velocity here is, let's say this is 5 meters per second, and the maximum, let's say 7, and this value is, let's say, equal to 6 meters per second. You can say that the average acceleration, let me write it down here, the average acceleration from t equal to 1 to t equal to 6 is simply 6 minus 5 divided by the time difference. The time difference is 6 minus 1. So 1 over 5 meter per squared second. So you probably noticed that the unit for acceleration is meter per squared second, which is actually the way to interpret acceleration is like this, based on the unit. Like let's say 2 meter per second squared or per squared second. Now you can understand this as 2 meter per second, which means that the velocity increased by 2 meter per second every second. Yeah. So, but then usually we just write it as this, but you need to understand why the unit is 2 meter per second squared. This actually can be understood as I mentioned here, 2 meter per second. So the velocity increased by 2 meter per second every second. Now, what about the instantaneous value? The instantaneous value is actually similar, which is, in order to calculate instantaneous acceleration, we need to know at what point do we want to evaluate the value. the instantaneous value. Now what we can do is, we can, let's say, oh, I want to find the acceleration when the t is equal to 2. So what I need to do is that in the graph, find when t equal to 2 and locate the position, let's say here. So this is t equal to 2, and then from here, what you need to do is you need to draw a straight line, a tangent line to the graph, and then estimate the value of the gradient. Yeah, estimate. So then in questions, in tests or exams, usually what we do is that we estimate based on the label. Usually they will tell you what the label is, then you can actually calculate rise over run to find out estimation for the instantaneous acceleration. Lastly, let's talk about graphical relationship between displacement, velocity, and acceleration. Well, earlier when we discussed about the definition of velocity, average velocity, acceleration, average acceleration, we actually learned a thing or two about the graphical relationship. But let's explain further here. Yeah. So if you have position or displacement function time, let's say like this. Yeah. Now what you can do is you can find the velocity at any instant by drawing a tangent line at that particular instant, and then you estimate the slope of this tangent line. Now you can see that this is probably not too accurate, yeah, but remember this is just estimate. So let's draw a bit closer so that the tangent line actually touches this point, like this. Okay, so you can see that at this particular time of interest, this is t equal to t1. Let's say we want to find the velocity at t1. All we need to do is we draw a tangent line of the graph at t equal to t1, and then you estimate the slope or the gradient of the tangent line. Yeah, so then velocity, yeah, equal, or instantaneous velocity equal to the slope or the gradient, yeah, of the tangent line to the displacement versus time graph, yeah, at particular instant. So what instant? At the instance when the velocity is us. Okay. Now what about if you have, let's say, velocity function time? Now when you have a velocity function time, how do you find, when you draw the graph, what can you deduce from that? Yeah. Now there are two quantities that you can deduce from velocity function time graph. The first one is this. The first one is if you, let's say, at a particular time of interest, t equal to t1, what we can do is we can draw a tangent line to the graph at t equal to t1, and this tangent line, from this tangent line we estimate the slope, again rise over run. Yeah, so you can say that the acceleration is equal to the slope or the gradient of the tangent line to the velocity versus time graph at particular instant. Now there's also another quantity that we can deduce from that, which is the area under the graph. Yeah, so if I have, let's say, let me redraw this velocity function. Let me copy this graph from here. So this is v function t. Now here, if we draw, let's say, from t1 to t2, let's say we draw an area below this curve of velocity function time, and there's an area. This area can be calculated. I mean, if the area is known or can be calculated, then what we can deduce is that the displacement can be obtained. So then the displacement is equal to the area under the curve of velocity function time graph. Yeah, from this time, this particular instant to that particular instance. Now you have to be careful when the value is negative. Yeah, although it does not appear to be commonplace in a lot of physics problem, but you also need to take into consideration what happens if the velocity, part of the velocity, becomes negative. Like, let's say like this. Now let's say that from this is equal to let's start from here, t1, and let's say this is t2 here, and then this is t3. Now what is the displacement from t1 to t3? Now in this case, because the velocity becomes negative, so what happens is that when velocity negative, that means that the object in one-dimensional motion has turn around and flip direction to the opposite direction from the original or from the initial direction. Now you can see that if, let's say that this is area 1 and this is area 2, then we can calculate the displacement to be A1 minus A2. What about distance? Now remember, for distance, it's always increasing. Yes? We always add up the length of motion, the length of the path of motion. So therefore, in this case, the distance is equal to A1 plus A2. So hopefully you know the distinction. Yeah. Even though a question like this is not very commonplace, yeah, in physics class, but just so that you know the difference. And last, let's talk about acceleration function time. So what do we get if we have acceleration function time graph? Okay, let me erase this part, yeah, the displacement function time graph, and let's talk about what do we obtain if we have acceleration as a function of time graph. When you have acceleration function time graph, let's say the acceleration is constant. Well, it doesn't have to be constant. Let's say it's constant in this case. Now, if you calculate the area on the graph, it will actually give you the change in velocity. Yeah, okay. So the change in velocity is equal to the area under acceleration function time graph. So let's say it starts from 0 and then it ends at whatever point t1. Then this area gives you the change in velocity. So I hope that you learned a lot in this video about kinematics. We will continue our discussion about a very special type of motion, which is called the uniform motion, as well as uniformly accelerated motion, in the next video. Don't forget to comment, like, and subscribe to this channel. I'll see you in the next video.